Hello everyone, Rashmita this side. Now I am going to discuss Hilbert space in this lecture, and in Hilbert space we will be using inner product space. So let's discuss inner product space. Let V be a vector space, or we can say linear space over a field K, real or complex. Let AB belong to K and UVW belong to V be arbitrary, then inner product. This particular function is called an inner product on V. If the following conditions are satisfied. The first condition is inner product of u comma v belong to K. That is, inner product of u comma v is a scalar quantity. Second property is inner product of au plus bv comma w is equal to a inner product of u comma w plus b inner product of v comma w. So this property is known as distributive property. Third one is inner product of u comma v is equal to inner product of conjugate of v comma u. We can say the complex conjugate of inner product of v comma u. Fourth property is inner product of u comma u is greater than or equal to 0, and also inner product of u comma u is equal to 0 if and only if u is a 0 vector. Okay, the vector space together with an inner product is called an inner product space, and also if the field is real, then we say it is a real inner product space. So it is known as Euclidean space. A real inner product space is called a Euclidean space. And similarly, if the field is complex, then we say it is a complex inner product space. Therefore, this complex inner product space is called unitary space. Okay. Now let's define Hilbert. Hilbert space, a complex Banach space Hk together with the complex function inner product of x comma y known as inner product is said to be Hilbert space if the following conditions are satisfied. The first condition is inner product of x comma y belong to K. The second condition is inner product of x comma y is equal to inner product of the conjugate, complex conjugate of y comma x. Complex conjugate of y comma x. Okay. The third property is, that is distributive property, alpha x plus beta y comma w, or you can say z, because here we are taking x, y, z. So this is equal to alpha inner product of x comma z plus beta inner product of y comma z. Now the fourth property, inner product of x comma x is equal to norm of x square for all x, y, z belong to H and alpha comma beta belong to K. Okay, so these are the necessary conditions for Hilbert space. The first condition is same, inner product belong to K. The second one is complex conjugate of y comma x is equal to inner product of x comma y. Third one is distributive property, and here it is norm of x square is equal to inner product of x comma x. So now let's discuss a linear product on H. Linear operator on H. Then its adjoint denoted by its adjoint denoted by T star is a unique operator on H, satisfying the condition inner product of u comma t v is equal to, or you can say inner product of t u comma v is equal to inner product of u comma t star v. Okay, so now we will be proving T star is a linear. To prove that T star is linear, so it is a linear operator, and for this, for proving T star is a linear operator, we have to prove T star of a v plus b w is equal to a T star of v plus b T star of w. So we have to prove this. Let's start from here. It's u comma T star a v plus b w is equal to, can be written as T, according to this definition, T u of AB plus BW. Okay, and now from here, using the distributive property, it can be written as T u comma AB plus inner product of T u comma BW. And now this A can be written as A bar inner product of T u comma V plus this B, since B is the scalar, T u of W. Now we know that T u of AB, since T u of AB is equal to a v comma T u conjugate. Okay, so now this can be written as A conjugate, and here it is V comma T, and finally it is A conjugate, and it can be written as T u comma V. So we are using the property of conjugacy over here, right? It can be written as this scalar A comes as A bar. Now this can be written as A bar, and again using the condition of adjoint T star V plus B star u comma T star W. Okay, and again we can say it is inner product of A T star V plus inner product of u comma B T star W. Now it can be written as inner product of u comma A T star V plus B T star W. Okay. The left hand side is inner product of u comma T star of A V plus B W. So from here we can say T star of A V plus B W is equal to A T star V plus B T star W. So we know that T star is a linear operator. And now let's find the angle between two vectors on a Hilbert space. Angle between two vectors, let theta be the angle between two arbitrary vectors, two arbitrary vectors x and y. Then inner product of cos, or you can say inner product of xy is equal to norm x norm y into cos theta, or we can say cos theta is equal to inner product of x comma y. So the angle between two vectors is given by inner product of x comma y divided by norm x and into norm y. Now if theta is 90 degree, particularly if theta equals to pi by 2, we can say x is perpendicular to y. X is perpendicular to y. Then obviously we have cos theta is equal to 0. So therefore norm inner product of x comma y is equal to 0. So we can say this is the condition of perpendicularity. Now if this is the condition of perpendicularity, then we can find some results. Let f and u is perpendicular to v. Then obviously we have already proved u equals to 0. Now the first result is u comma v is equal to 0 implies v comma u is equal to 0. That is, we can say if u is perpendicular to v, then v is also perpendicular to u. So now let's prove. We start from here. U comma v can be written as, you have to prove. So you can start from here also. V comma u is equal to, you can say it is the complex conjugate of uv, and inner product of uv is 0. So it is 0 bar, or it is 0. So proved. U is perpendicular to v implies v is perpendicular to u. Now the second result. Zero vector is orthogonal to every vector. Zero vector is orthogonal because this is a condition of orthogonality. Zero vector is orthogonal to every vector. Zero comma u can be written as 0 into 0 vector, and is equal to 0 inner product of 0 comma u, and 0 multiplied by the inner product is equal to 0. So this implies 0 is perpendicular to u. Now we can also prove the Pythagorean square plus g square. Okay, now we have m is perpendicular to g and plus g is perpendicular to f. Therefore, we can say inner product of f comma g is equal to 0 and inner product of g comma f is also equal to 0. Now we start from left hand side. It can be written as by the definition of norm in terms of inner product. Here we can use distributive property and again f comma f plus inner product of f comma g plus inner product of g comma f plus inner product of g comma g. Now f comma f can be written as now f square plus inner product of plus now g square. Now we know that these two values are equal to 0, therefore norm f square plus norm of g square. So we have proved that norm of f plus g is equal to norm f square plus norm g square. Okay, now let's continue this topic in the next video. Thank you.